Hey everyone! Another day, another lesson. So today's lesson is called LeChatelier principle. Obviously discovered by this guy named LeChatelier. Okay? And the whole idea here is what happened when there's an application to your equilibrium reaction. An application means what if you take certain things away while the reaction is happening? Or what happened if you decided to decrease the volume and increase the pressure? Or what happened when you add a catalyst? Will these things play a role in shifting your equilibrium? So you'll hear these words a lot. Shifting equilibrium, shifting forward, shifting backwards. Certain things increase, certain things decrease. So that really kind of mess with your mind. Okay, so here's a few things that we're going to see. Okay, we're going to see how concentration can affect LeChatelier principle, which means how concentration can actually make a reaction going forward or going backward depending on where the concentration is being increased or decreased at. We will look at pressure and volume. Hey, I hope you remember from a while ago that pressure is inversely proportional to volume, meaning that if pressure increases, volume decreases. Pressure decreases, volume increases. Now that's a very important point. I hope you remember all of that. Then there's temperature. What happened when there's a change in temperature in your reaction? Because you're talking about temperature, mind you gotta have to talk about energy. So this guy comes back and stick out his ugly head. So let's go. Let's take a look at LeChatelier principle. But first, number one, we're looking at changing in concentration. What happened when concentration changes? Now, when you think of concentration, think of it as amount. What happened when amount of something is taken away or amount of something is added? Think of that. Okay, I know when you think of concentration, you think of solute over amount of solvent. Don't worry about that. Think of just things you're putting in and things that you're removing. So addition or removal of either reactants or product will shift the equilibrium. Okay, and which way does it shift? Well, it all depends. Remember last class we took a look at a certain variable that I introduced you to that will test the fact, if the reaction is going to go forward or going backwards? That's right, we learned about QC. So let's take a look at this little example right here. Okay, I have this reaction where you're making ammonia by combining nitrogen gas and hydrogen gas together, and this reaction is actually an equilibrium reaction. Okay? This is the equilibrium concentration, which means at this concentration, this is at equilibrium because QC is indeed 0.291. This is good. The rate of this is equal to the rate of that. To achieve that, N2 has to be 0.5, H2 has to be 0.3, and NH3 has to be 1.98. Well, guess what? Guess what I'm going to do? I'm going to do something bad. I'm going to take some of these product away. Imagine this is an assembly line and you're making NH3. Every time you make NH3, some dude would go, yoink, let me take some away. Let me take some away. Let me take some away. As a result, you're left with a lower concentration of NH3. Because every time these things are made, you took it away. How much did you take away? Well, you took away 0.99 of it. Now, take a look at your equilibrium. Let's take a look at a QC. If you do a QC for this data right here, you'll notice that QC is going to be 0.073. It's going to be smaller. So what happened when your QC is smaller? Well, the reaction will proceed forward, right? That means you don't have enough numerators, which is here. So the reaction will go forward. What does that mean? That means if you have a reaction like this one, and you keep taking away products physically, sort of like a mouse taking chocolate bar away from a chocolate assembly line, then the reaction will think to itself and say, oh, we don't have enough products to reach equilibrium. Oh, okay, let's pump more. But as you pump more, that mouse keep taking it away. So you keep pumping, and they keep taking, keep pumping, and keep taking until somebody says, stop taking. You will pump and pump until it reaches equilibrium. But as long as you take away the product, reaction will continue to shift right. Let me say that one more time. As long as you take away product, reaction will shift right. Because reaction will always try to achieve equilibrium situation. You take away product, you're lowering the numerator. Lowering the numerator will give you a QC that did not reach KC, so the reaction has to proceed forward. You didn't understand that? Maybe try to rewind and see if you can understand that again. But that's exactly what happens when you increase decrease the concentration of NH3 by taking some of the products away. So let's take a look at the second situation, example 2. Take a look at this. What you're doing here is you're supplying more reactants. So what we did is that we took one of the reactants and we supply, let's say, more. So remember, this was the equilibrium situation. This is the, alter situation. And how do we alter it this time? This time, I'm not going to take products away. I'm just going to keep injecting reactants. Well, when you do that, you're actually making your denominator bigger. When denominator gets bigger, your overall QC is going to be lower. Low enough that it's going to be less than KC. Less than KC, forward. Okay? Which makes sense. You keep supplying stuff to make NH3. This will say, okay, I'm going to continue to go. I'm going to continue to go. As long as I have enough of this, hey, as long as I have enough of the other ingredient, I'm going to continue to move this direction until this goes to 0. Because you're supplying so much of this. Right? It's almost like making bikes. Here's frames, you're making frames, and here are wheels. You keep supplying frames. You're going to be using up these wheels and using up these wheels, making more bikes. Yeah, you're probably thinking, that doesn't look like a frame. That doesn't even look like a wheel. But that's how it works. That's the LeChatelier principle based on concentration. Let's review the first example and the second example. You take away products, reaction proceed forward. You add more reactants, reaction proceed forwards. Simple. Simple, simple, simple. Here's another situation. Let's take a look at this situation. Oh, okay. Okay, let's take a look. Again, this is the ideal situation. And in the alter situation, it looked like I decreased some of the amount of the reactant. I took some of the reactants away. Make it lower. Well, mathematically, if you make it lower, any one of these, your QC will be bigger, because if you are decreasing your denominator, obviously your overall answer will be bigger. Bigger than KC in this case. Hey, if that's the case, reaction is going to shift backwards. They're going to say, oh, wait. We like it when it's 0.5 here, 3 here, and 1.98 here. But if you were to drop this to 0.25, I'm sorry, but I'm just going to have to go back and give some more back to N2 so the ratio balance out more. Hopefully you get what I mean. Okay. And last scenario. Oh, let's summarize this scenario first. So if you take away reactants, reaction will shift to the left. All right, one more. After this, we're going to go and look at another scenario, I guess. Again, this is your ideal. That's 4 times I said that. And take a look at this. You know, before we had that mouse taking away the chocolate bar? But what if we do this? What if we physically add products in there? I said, oh, I found some NH3 here in the storage room. I'm going to add it to this reaction vessel and see what happens. Well, what happened is that now you have too much NH3. It's not balanced anymore because now the numerator is getting bigger. Right? Numerator get bigger. Your QC gets bigger. It would be bigger than KC, so the equilibrium says, oh, you have too much product now because you're, disturbing it by adding more product physically. That's not good. We're going to shift things back because we like it at this ratio. You make this big, no big deal. Now just go back and make more of these. When will you stop? I will stop when I reach KC looking like that. So those are the 4, I guess, scenarios. Okay, so let's kind of summarize this a little bit. So when this increases, the reaction will proceed backwards. Okay, when this decreases, the reaction will also proceed backward. So that's concentration. Okay, in terms of LeChatelier principle. It's very important. So make sure you try to understand all 4 of that scenario for this type of change, dealing with concentration. So let's take a look at another entity. Changing of pressure and volume. Now this has something to do with concentration. Because if you were to look at this under a cylinder and piston apparatus, usually for this, you're talking about gas, because only gas can you kind of play with pressure and volume like that. So when you have an increase in pressure, so when this piston increase in pressure, you can see that the volume will decrease. There's going to be less space for these gas to move around. Now, if you think about it, less volume. Oh, if volume is being decreased, won't that make concentration increase because you have less volume? Because we know that concentration is the amount of mole over volume. If this number is getting smaller and smaller and smaller, that means this number is getting bigger and bigger and bigger. So pressure and volume changes concentration. Hence, we said right here that pressure and volume are inversely proportional. Okay? And a decrease in volume, like I illustrated, okay, if you make volume going smaller, the concentration will increase. You'll get more in terms of the concentration. Okay, remember, when the concentration is higher, these gas molecules are going to hit each other with more force, if you remember. Okay, forces that will go over the EA, which is your activation energy barrier, more easier. See how all of this chemistry all ties in together? Chapter 5, 6, and 7. It seems like they're all friends. Okay? So, because of that, if there is a decrease in V, this will actually shift the equilibrium to the side with the least number of mole of gases. What does that mean? All right, here's an example. Here's an example right here. Determine the effect of a 2 times increase in pressure. So you're increasing the pressure 2 times, which means the volume will be decreased by a half of the original. Hope you remember this guy. I spelled his name wrong. Boyle's law. Okay, so if you double the pressure, the volume will be a half. The concentration of the reactants and product will also decrease by a factor of 2. So if you lower the volume by a half, your reactants, your concentration will be increasing in a factor of 2. If QC now is smaller than KC, the reaction will proceed right to form more NH3. So let's take a look at what I have over here. Okay, so again, this is the original situation, the ideal situation. Because of the increase in pressure in this vessel, because of the increase in pressure, you can see that the concentration has actually increased because volume has decreased. And this guy. Because they're both increasing, okay, not just that, but also the product is also increasing because there's less room. You'll notice that QC will therefore decrease. Okay, decrease enough that the reaction will actually go forward. You're gonna have to pump some more because there's a decrease in QC. Now, why would there be a decrease in QC? This is the kicker right here. This sentence pretty much dictates exactly which way the equilibrium constant will shift. Okay? A decrease in volume, which is exactly what happens here, shift the equilibrium to the side with the least number of moles. Shift to the side with the least number of moles. How do we determine that? This will be determined by the equation itself. Is a 1 here? Is a 3 here? In total, that's a 4. Let's look at the right side. Is a 2 here? Which one is lower? Of course, 2. Then it shift this way. Just like what it says. Just like what it says. Okay? If volume decreases, the side with the least number of mole is where the equilibrium shifts to. The total mole here is a 4. The total mole here is a 2. You're going to shift this way. So this will go less. This will go more to get back to where you're at. Pretty cool way to think about. Okay? So for the same reaction, if you were to decrease the pressure, by decreasing the pressure, you're actually increasing the volume this time. So if you're increasing the volume, hey, it only makes sense, of course, that the reaction will go the other way. Okay, so when you're increasing the volume, it will shift to the more number of moles. So we'll go this way. All right, it's pretty easy. Pressure and volume is the probably easiest one to figure out if it's which way it goes. All you have to do is just look at the total number of moles. Okay, just by looking at the equation. All right, so I pretty much already explained this. So if there is a decrease in pressure, okay, especially if the decrease is a factor of 2, so you're pulling up the pressure in a factor of 2, then of course you're going to have more volume, right? 2 times more volume in this case. So having 2 times more volume, then QC in this case will be higher, as you see right here. But really all you need to know is that this is a 1, this is a 3, so it's a 4 to a 2. So in this case, it will go towards that way. Okay? All right. Oh, I have a question right here, so make sure you do that. Okay? Here's a question about change in temperature. So we looked at change in concentration, then we looked at, of course, change in pressure and volume. So what about if there's a change in temperature? You have this reaction going on and you decided to heat it up. Oh, why would you do that? Well, by doing that, or not, maybe not just heating it up, maybe you, for some reason, you drop a couple of ice cubes in there and cool it down. Since we're talking about temperature, if you're talking about temperature, you must be talking about energy, because that's what temperature is measurement of the kinetic energy in a system. Oh, that is so thermodynamic type of saying. Okay, so let's take a look at a reaction right here. Let's take a look at a reaction. Because it's said that an increase in temperature increases or decreases the amount of CO produced from the following reaction. I have this reaction. It's an endothermic reaction. That is a very important thing to know, meaning that this reaction absorbs heat, making the surrounding cold. Okay? And what am I going to do? I'm going to increase the temperature in the surrounding. I'm going to increase the temperature in the surrounding on a reaction that absorbs heat. So I have fire here. And this reaction says, you know what? I absorb heat, you know. You provide me with heat, I'll absorb whatever you get. Why? Because naturally, I'm an endothermic reaction. Well, since the reaction is endothermic, adding heat will allow the reaction to absorb it. You give them heat, I will take it. I like to take money. I like to take ching ching. You supply me with a lot of ching ching. You give, I take. You give more, I take more. Therefore, because of that, this idea will drive the reaction forward. You give me energy, I take. Now I have enough energy to go this way. Why? Because I am endothermic in nature. That's what I do. I take. Makes sense? What if I don't take? What if I'm this reaction and I release? I'm one of those that nature's love. I release energy to the surrounding because I am exothermic in nature. Well, what happened if I release this heat and I have money going on here? Okay, I have a fire going on here and I'm increasing the temperature of my surrounding while this guy is also increasing the temperature of the surrounding. It's almost like, I don't take money. I give money. And you have this fire saying, I give money too. You give money. I give money. What's going to happen? Well, what's going to happen is that you're going to drive this reaction backwards. So for an exothermic reaction where you're already releasing heat, by inputting more heat will drive the reaction back. Because the reason why this thing is giving off heat is because it's driving forward. Because every time you make NH3, you release this heat. Well, because the outside temperature is already so damn hot, this reaction will say, oh, I think the surrounding is hot enough. Let's not make so much NH3 anymore. Let's go back. Let's go back. Because we don't need to generate more heat. The surrounding is already hot enough. Remember, back in thermochemistry, what happened when you reverse a reaction process? That's right. Delta H times -1. Negative 92 kilojoule becomes 92 kilojoules. So instead of making the surrounding extra hot, I'm going to go backwards. Okay? I'm going to be endothermic to kind of counteract with the hotness that is being inputted into the surroundings. Again, it makes sense. Here's a little chart to kind of summarize everything. So this is actually something that I think you guys should try to, I wouldn't say memorize, but totally understand. Okay? So again, let's go with exothermic. So if you're at an exothermic condition, by increasing the temperature, we saw that it will favor reactant. This is already giving off heat, and you're giving off heat too. You know what? I think I get to stop producing more heat. I'm going to go backwards. Okay? However, if you're an exothermic reaction, which you're giving off heat, and I decrease the temperature, let's say, oh no, I'm going to have some ice cubes here instead. So exothermic reaction will say, whoa, man, the temperature is cold out there. Let me give off more heat by generating more products. Same with this, okay? I absorb heat. I absorb. You increase the temperature, you give, I take. By taking, I'm making more product. Same with the other way around. I'm making the surrounding cold by taking heat in. You lower the temperature outside. Well, it doesn't make sense. I'm already making the place cold and you're making the place colder. I guess I'm going to have to go backward and release some heat. To do that, I need to go this way. Hey, I hope this chart makes sense to you. And lastly, before I call it for the day, what about catalysts? What if I have a reaction, an equilibrium reaction, and I add a catalyst because I don't think this reaction is going fast enough? Guess what? Catalyst has no effect on equilibrium. Not at all. In fact, it speeds up the reaction to reach equilibrium. Right? I will get to the equilibrium faster, and that's what I'm going to do. So, because of that, mathematically, Kc is definitely related to delta H, as we saw right here. But it has nothing to do with EA. Getting through that equilibrium activation energy hump. It has nothing to do with equilibrium. All right, so that's it for equilibrium, actually. Okay, we're done with chapter 7. Next is actually chapter 8. Now, we already did a little bit of chapter 8 when we were looking at chapter 1. remember solutions and stuff like that. And then we looked at acid and base for a while. We did some titrations. We did some pH calculations. Well, we're going to do the missing part of chapter 8 that we say, yeah, we'll do later. After we learn about chapter 7, after we know everything about equilibrium, we are going to go back and look at chapter 8. And that's what we're going to do. So in the meantime, okay, try to understand LeChatelier principle, and I'll see you later. Bye.